about game theory. And we covered von Neumann-Morgenstern, their theorem and the utility function, correct? For wealth? You don't remember? That's okay. You do remember the St. Petersburg paradox, right? That was the gamble. Yeah. Okay. Okay. Well, the von Morgenstern theorem is basically the following. You have a bunch of prizes, right? And a lottery where you can win those prizes. And you arrange the prizes in order of the least valuable to the most valuable. So you have x1 through xn, where x1 is the least desirable and xn is the most desirable. And then we're going to standardize the utility that you receive from the best prize and the worst prize. So the utility for winning x1 is 0, and the utility for winning xn is 1. So now what I want to do is I want to have these players assign subjective probabilities, what they think the probability of winning x1 is and what they think the probability of winning xn is. And if they only had those two, what would be the probabilities, their subjective probabilities? And I'll denote that by pi. So pi I. So pi I times u of xn, that's equal to 1 for us, or will be, and 1 minus pi I times u of x1, which we saw before was 0. So I have pi 1 plus 1 minus, I didn't even touch it, 1 minus pi times 0, and all of that, we end up with pi, which, by the way we set it up, right, shows that the utility number attached to the game is simply the probability of winning the top prize, right, pi. Okay. So the individual regards receiving this amount with certainty, right, as equivalent to playing the game in question because they both give the same utility. Okay, now what we're going to do is we took the game and we changed it. We took away all the other prizes except the top and the bottom. Now we're going to start adding back in the middle prizes and play the same game with middle prizes. Right? So I'll start with 2 middle prizes, call it x2 and x3. And in this gamble, you can win x2 with probability q, right? And x3 with probability 1 minus q. Again, we have a game. And I have that game, and then I'll set up another game with 2 other middle prizes. We'll call it x5 and x6. And you can win x5 with probability t and x6 with probability 1 minus t. So therefore, the expected utility for winning the first gamble is right here, q times ux2 plus 1 minus q times ux3. And the second one is t ux5 plus 1 minus t ux6. And therefore, right, since we saw that we can simply insert the probabilities in that first part, we're going to do the same thing. So I have q times pi 2 plus 1 minus q times pi 3, where with our logic, pi 2 is equal to the utility of x2 and pi 3 is the utility of x3. And I do the same thing for x6 and x5. So I get t times pi 5 plus 1 minus t pi 6. Okay. So I can say that the gambler will prefer gamble 1 if q pi 2 plus 1 minus q pi 3 is greater than t pi 5 plus 1 minus t pi 6. And I could do the opposite. I can switch that greater than sign around, and that means he'd prefer gamble 2. Right? And that's basically all the von Morgenstern theorem is. Right? It's just setting up a game and showing that, right, the player will prefer the way he ranked it, the better prizes to the lower prizes, and he'll prefer the gambles with the greatest expected utility. Pretty straightforward. Okay. So now what I want to talk about is risk aversion, or aversion towards risk. I'm going to set up a gamble graphically. Suppose I have wealth W and I set up a gamble where there's a 50% chance that I win an amount, I'll call it H, or I lose that same amount, H. Right? I set up another gamble where again there's a 50-50 chance where I win 2 times H or lose 2 times H. Right? So my utility from that first gamble, since it's 50-50, is 0.5 W star plus H, where W star is the wealth I start with. H is how much would add to my wealth if I win. And the second part is 0.5 U W star minus H, and this minus H, this is if I lose. And then the utility from the second gamble, U2H W star, is 0.5 U W star plus 2H plus 0.5 U W star minus 2H. Right? If the utility function is concave, right? And when I say concave, is I set up a graph with utility on the vertical axis, right? And the prizes on the horizontal axis, or I'm sorry, not the prizes, the wealth, it's wealth on the horizontal axis, right? If it's concave, then this person will have the following preferences. He'll prefer not taking the gamble to taking the first gamble, whether he wins or loses H, and he prefers that first gamble where he only wins or loses H to the gamble where he'll win or lose twice that much, 2H. And of course, UW star is the utility received from the certainty equivalence of the 2 gambles. In other words, not gambling at all. Okay, so here's our graphical representation. Like I said, we have utility on the vertical axis, wealth on the horizontal axis. So if this person is forced to take the first bet, right, W star, right, his utility is going to be as follows. This is his utility curve, or his utility function, right? If he wins H, this is how much utility he gets up here, right, which would be greater than, obviously, than not taking the gamble if he wins. But if he loses, right, and this dot, it got put in a spot where it shouldn't, but if he loses, it's this line down here. And if you remember the definition of concave is simply that if I connect 2 points on the curve, it's going to lie below the graph, which this one does, right? It lies below the graph. So his expected utility, right, is going to be at that level, that red dot right there. And then I go across, and therefore the utility from this first gamble is right here, and it's below not taking the gamble, right? So here, right, this person is worse off because he doesn't want to gamble. Now, this person would actually be willing to pay to avoid this gamble. You can think of it as insurance. And the amount he'd be willing to pay is, now pretend that this line over here is actually on the curve where the dot is, but the amount he'd be willing to pay, right, is W bar, right? Or I'm sorry, that's how much his utility would be from this gamble if he didn't, in other words, if his wealth was W bar, right, and he didn't have to take this gamble, or and he was forced to take the gamble, those 2 utilities would be the same. In other words, forcing him to take the gamble and just giving him W bar would give him the same utility. So he's willing to pay the difference, W star minus W bar, to avoid the gamble. And of course, this other one, I didn't do it because I didn't do how much he'd be willing to bet or how much he'd be willing to pay to take the gamble. But it's essentially W star times W minus H, which just happens to be where that dot is, just because I was running out of room where to put stuff on the graph. It doesn't necessarily be there, but it would be that same amount here or very close to it, where that dot is, and that's how much you'd be willing to pay to avoid taking the second gamble. Of course, in the second gamble, if he wins 2H, his utility is way up here, and of course, if he loses 2H, his utility is way down here. And the average of those two is that straight line, which puts him right here, which is way below, or farther below, the certainty equivalence of not gambling at all, right? So the individual who always refuses fair bets is said to be risk averse. That means when we draw the utility function like this with respect to wealth, right, it's going to be concave. That person's risk averse. If the individual exhibits diminishing marginal utility of wealth, which this person does, right? In other words, as his wealth increases, his utility increases, but at a decreasing rate. In other words, the second derivative is negative. So this person, by definition, is what we call risk averse. And they'd be willing to pay something to avoid taking the fair bet, or they'd be willing to pay for insurance. Okay. The next example we have is a utility function that's convex, right? In this case, that second derivative would be positive. So you have the first derivative positive, second derivative positive, right? And in this case, right, the average of the two bets, right, if he wins the bet, his utility is way up here, or if he loses the bet, it's way down here, but the average ends up being above the certainty equivalence, which is right here. So the average, or the expected gamble of the bet, gives him more utility, more expected utility. Huh? Yeah. There you go. So he gets more utility from taking the gamble than he does just keeping his wealth at W star. And he'd actually be willing to take this bet. He'd actually be willing to pay the casino to make this bet. And the difference, or the amount he'd be willing to pay, is the difference between W bar, which would be the equivalent if you just give him that much or give him the option of taking the bet, minus W star. That's how much he'd be willing to take the bet. Questions? So finally, right, we've had diminishing marginal utility of wealth. We had increasing marginal utility of the wealth. Now we have constant marginal utility of wealth, right? We have the straight line. And this person really doesn't care if he takes a gamble or not. He's indifferent, right? Because that straight line in between the two dots is right on his utility curve. So he's indifferent between taking the two, and we call those types of people risk neutral. He doesn't care if he takes a bet or not. His utility is the same. Questions? Okay. So given those, a guy named Pratt came up with a way to measure risk aversion. Right? We know if somebody's risk averse, that second derivative is negative and that first derivative is positive. So we just got to figure out how fast you have that diminishing marginal utility. In other words, what's that rate? So what he does is take the second derivative and divide it by the first derivative. Of course, that second derivative would be negative for a risk-averse person. So negative and negative would be positive. So for a risk-averse person, the Pratt risk aversion measure would be positive. For a risk-seeking person, it would be negative. So U double prime, of course, is the second derivative with respect to wealth, and U prime is the first derivative. And as I said, since U double prime is negative for risk-averse agents, right, the risk-averse measure will be positive. Okay. So let's talk about insurance premiums. To do this, I have to either remind you or introduce the concept of a Taylor series expansion or approximation, right? So let's start. Consider a fair bet, sort of like we did in the graph, of H. So you either win H or lose H, so the expected value of the bet is 0, right? I'm going to let P be the amount where the player is indifferent between taking the fair bet or paying a premium. So P would be the premium where he's indifferent from taking insurance or taking the fair bet. And therefore, we'll do the situation as follows. E, U plus H, we're going to, the expected value of W plus H is going to be equal to U, W plus P, where W is the individual's current wealth, right? And of course, P, like I said, would be that premium that makes you indifferent. Darn it. Touch it. So we're going to use a Taylor series approximation. And if you haven't seen it or you have way back when you took calculus, it's if you have a function of x and you add to it just a little bit, you can approximate the value of the new function as follows. I'll take f of x, just f of x, plus h times f prime of x. In other words, h times the first derivative, that first change in x, plus h squared divided by 2 factorial times the second derivative of f of x, h cubed plus 3 factorial times the third derivative of x, and then you can do the same thing, just keep going. You'll have h to the 4 times 4 factorial, fourth derivative, and so on. As many derivatives as are possible. And you can do a Taylor series approximation basically to infinity if there are that many derivatives. I don't think there's many functions with that many derivatives, but or that many orders of derivatives. Anyway, that's a Taylor series approximation. So what we're going to do is for u, w minus p, I'm going to use a first order Taylor series approximation. It's very simple. It's just u of w minus p u prime of w. And then for the second equation, that u of w plus h, or the expected value of u w plus h, I'm going to use a second order Taylor series. Now, why am I doing first order and second order? Because it works is the short answer, right? Because we want as many variables as unknowns, and that does it for us, right? And they're both approximations. The second one's obviously a little better than the first, but they're approximations. So that first one, the first one we have up here, u w minus p u prime. For the second, I have the expected value of u w plus h u prime w plus h squared, 2 factorial. What's 2 factorial? 2 u double prime of w. So I can expand that. So the expected value of uw we already know, so it's just uw, and we know the derivatives of the utility functions. What I don't know is h. So I have, actually we do know expected value of h. I don't know the expected value of h squared, but we'll talk about that in a sec. So uw plus expected value of h, u prime plus expected value of h squared over 2 times u double prime. Now, if you remember, we assumed, because it's a fair bet, that the expected value of h was 0, right? So taking that fact that u of h is 0, I basically equate the two Taylor series approximations, right? So this is approximately equal to this. That's at uw plus 0 plus the expected value of h squared divided by 2 times u double prime w. Now, this is simply a constant, right? H is constant. So I'm going to denote this expected value of h squared divided by 2. I'm going to denote it by k, right? So I solve for p, the premium, right? So therefore, the premium is going to be approximately minus k times u double prime over u. And of course, minus u double prime over u is simply our Pratt risk aversion measure. And we get k times the Pratt risk aversion measure. What that shows is the amount a player is going to be willing to pay for insurance, or the premium he's willing to pay, is going to be proportional to the Pratt risk aversion measure, assuming you have at least 2 derivatives in his utility function. Questions? Why are you looking at me that way, Daniel?
Estoy tratando de seguir, pero el detalle está chévere, pero ¿cómo tú sacas la utilidad de la persona?
Bueno.
En la ecuación, entonces, ¿cómo sacas la derivada? O sea, la derivada es fácil, pero sacar la utilidad de la persona.
Como te digo, conceptualmente la podemos hacer. Yo no te puedo decir la utilidad de cualquier de ustedes. I have no idea. Y en realidad, tu utilidad probablemente cambia de un momento a otro. Y como dije, el primer clase que estamos hablando de la teoría del consumidor, pues esa es una de las suposiciones que hacemos, que la utilidad se queda fija, a lo menos por el tiempo que estamos analizando, ¿no? And basically this is theoretical. When we talk about utility, there's no way to measure utility. I don't know how much satisfaction. I can't say that you like blackjack more than he likes blackjack because I don't know your utility function. You might spend all your time at the blackjack table, but the utility for him might be greater than you. It's just that he has more utility for other stuff. There's a ton of nuances. Again, this is theoretical. But the concept is sound, right? In other words, the premium is going to be proportional to some measure of risk aversion if we can measure risk aversion. Okay, and getting back to that, here we have three utility functions, and they're all concave. In other words, these people with these utility functions are risk averse. So the question is, does risk aversion increase or decrease with higher levels of wealth, right? And it depends on what assumptions you make. For the first one, the richer you are, the more risk averse you become. The second one, the less risk averse you become. And the third one, you really don't care. The richer you get, your risk aversion stays the same. Now, it doesn't mean, like, for instance, if you're not willing to gamble or you'd get utility from gambling on some small proportion of your wealth just for the utility of the game. For instance, buying a lottery ticket. You buy a lottery ticket, it's possible that utility from buying that lottery ticket, since it's such a tiny portion of your wealth, is positive. And obviously it is, otherwise you wouldn't buy the lottery tickets. Okay. Questions? Okay. So taking that Pratt risk aversion measure, I'm going to go ahead and multiply wealth to it, and I'm going to call this relative risk aversion. This tells me how risk averse I get in proportion to my wealth. So if risk aversion changes are roughly proportional to the wealth, then my relative risk aversion measure will be constant. If my risk aversion increases when my wealth increases, then positive. And if it decreases faster, slower than if it increases slower than my wealth, then basically as I get richer, I become less risk averse. Just like those functions that we saw on the previous slide. Okay. So now I'm going to take all that and I want to basically, instead of doing it, well, it's still kind of theoretical, but I'm going to apply it to something that's closer to the real world and insurance premiums. I'm going to assume that I can categorize the world into states of nature, right? In other words, that there's a bunch of states, and in those different states, my payoff is going to be different. So assume all outcomes of many random events can be categorized into a number of states of nature, states of the world. So it's possible to assign probabilities to all those states, right? For instance, tomorrow the stock market will be up 1 cent, 2 cents, 3 cents, 4 cents, or down 1 cent, 2 cents, 3 cents, 4 cents, and assign probabilities to all those things, right? Obviously, there's an infinite amount, and all those probabilities are small, but I can group them together to make it a little less cumbersome. But all those states of nature, right? It's probable for me to come up with basically a probability function that covers everything that might happen tomorrow in the stock market. I can do the thing for the whole world, for every market. Then again, it becomes overly burdensome or overly cumbersome for us. But theoretically, it's possible, right? It might be possible, however, to insure against all these states of nature. For instance, if I'm shorting, I don't want the market up, or if I'm long, I don't want the market down. It might be possible to insure against those things. So if we can ensure that I'll receive extra wealth when things go bad for me, right? Where my wealth will otherwise be low. This can be thought of as a contingency commodity or contingent commodity. The commodity can insure against or ensure constant wealth no matter what happens in the market. In other words, in this case, right, we have an insurance market for the stock market. It's the derivative market. So the commodity can insure against wealth in all states of nature, if desired, or simply lessen the burden of bad times. So instead of an infinite amount of possibilities, let's break it down to two. I have a good state of nature or a bad state of nature, right? And I'll denote G for good times, B for bad times. So WG will be my wealth in good times, WB will be my wealth in bad times. I'm going to assume that utility depends solely on wealth. And implicitly, that's what we've been doing this whole lecture. And that the subjective probability of good times occurring is going to be pi, right? So the expected utility associated with the two contingent goods is pi times my utility in the good state plus 1 minus pi times the utility in the bad state. So the price of this insurance or this contingent commodity, I'm going to assume that the person purchases or sells $1 of wealth in good times and $1 of wealth in bad times. So for good times, I'm going to denote that as PG. And for bad times, I'm going to denote it as PB, right? So I can write the constraint as W is going to equal PG times W of G plus PB times W of B, basically ensuring in this case that my wealth stays the same no matter what happens. Now I'm going to change that up just a little. As before, right, I'm going to assume that the ratio of prices of good to bad, I told you we should have waited, guys. Okay. Anyway, the ratio of wealth for good to bad is PG over PB. Now with fair insurance means I just pay, right, the difference in expected values. That's what fair insurance means. In other words, in this case, on average, the insurance isn't making money off me. But with fair insurance, a person could give up $1 of wealth in bad times for $1 of wealth in good times. Now that's opposite of what we usually think, right? But I think your book does it just so you can get the concept and not denote on when things are good and when things are bad. So if I have fair insurance, the ratio of prices will equal the ratio of the probabilities of being in good times relative to bad times. And we can do math to do that. As PG over PB is going to be pi over 1 minus pi, right? The price, therefore, of buying $1 of wealth in good times is equal to the probability that good times will occur, and therefore the price of buying a wealth in bad times will be equal to the probability that bad times occur. So PG is equal to pi, PB is equal to 1 minus pi. So I can think of this as giving up PI to get $1 in state I. Think of it as an insurance pool, a gambling pool, right? So if pi equals PG equals 0.75 to get that $1 in good times, then, and I pay that 75 cents, the 75% of the people that end up in good times, right, pay 75 cents to get $1, but those people that aren't in this insurance pool end up in bad times, don't get anything. Doesn't kind of make sense, but we can flip it over. Alternatively, a pool can exist where I pay a quarter, 25 cents, to get $1 in the bad state. And in this case, the 75% who end up in the good state don't get anything. But the people, right, who who end up in the bad state get $1, or the 25% that end up in the bad state get $1. So in that case, it's insurance against a bad state. So now we can show that if insurance is fairly priced, like I defined it, a utility maximizing agent, right, will have the same wealth in good times and in bad times. Right? To see this, right, consider the marginal rate of substitution between wealth in good times and wealth in bad times, right? And just like when we did our theory of the consumer, right, that marginal rate of substitution has to equal the ratio of prices, PG over PB. So my marginal rate of substitution, the partial of my utility over my wealth in the good times, is pi times U prime WG. And the same thing for bad times is 1 minus pi, the probability of being a bad time, U prime WB, the wealth in bad times. And that's equal to the ratio of prices, PG over PB. So remembering the relationship between the price ratio, PG over PB, and the ratio of probabilities, pi over 1 minus pi, I flip them over, and what I get, right, I take this pi and bring it over here, and PG is equal to pi, so they cancel. 1 minus pi is equal to PB. I multiply both sides by m. This goes away. I have 1 minus pi over PB, and they cancel. So I end up with U prime WG over U prime WB is equal to 1, or what we set out to prove is that in this case, the wealth in good times will equal wealth in bad times with the fair insurance. Okay, so graphically it looks something like this. I have wealth in good times, across the horizontal axis, wealth in bad times. I have my utility function that gives me, or basically an indifference curve between wealth in bad times and wealth in good times. And I end up right in the middle, right there. In other words, array a 45-degree line ending up in the origin, and this will be my budget constraint. Then with what's going to be the slope of that budget constraint? Maria's going to tell me. What? What's the slope of that budget constraint? Okay. Okay. What was the slope of our budget constraint when we started with consumer theory, where we had, instead of wealth, we had two goods, right? Okay. And now? Okay, but that's not the prices. Those aren't prices. Those are wealth. So Deanna's going to tell me, right? I can see it in her face. She knows. No? Okay. The slope of this budget constraint, I. Eh? Okay. Well, you guys just told me that the budget constraint, the slope of the budget constraint, when we're doing regular consumer theory, where instead of WB and WG, we had two prices, the price of X and the price of Y. You told me that's the ratio of prices, PX over PY. Okay. The indifference curve. Okay. No, they're equal. That's perfect. But what is it in terms of my ratio of prices? Okay. Well, we can denote it in pi, but right now I just want it in prices. Because we saw that with fair insurance, right? The probability is equal to prices. But here, what's the slope? Actually, that's correct, but that's not what I'm looking for. PG over PB. There we go. Right. And that's going to equal pi over 1 minus pi, because PG is equal to pi and PB is equal to 1 minus pi. So yes, the slope, right, of this indifference curve is the ratio of prices, PG over PB. I have another indifference curve here, I prime, when insurance isn't fairly priced. And in this case, according to this slope, right, where it's equal to our indifference curve, is over here, where we end up with more wealth in the good state and less wealth in the bad state. In other words, when we don't have fairly priced insurance, right, we only partially insure the bad state. Okay. So in that case, P prime of G is going to be less than pi, and P prime of B is going to be greater than 1 minus pi, right? Because we don't have fairly priced insurance. So with the new prices, the marginal rate of substitution is going to be smaller, less steep, or more flat. And the agent insures less than 100%. In other words, he'll choose to have less income in the bad state than in the good state. Okay, so now let's go through some examples. Suppose I have a consumer whose utility function is as follows. It's simply the natural log of his wealth. Suppose that the probability of good times is 0.75, the probability of bad times is 0.25. So therefore, the expected utility of an agent, if the following is true, if income in the good state is 100,000 and income in the bad state is 80,000, I can write his expected utility as pi times the natural log of wealth in the good state plus 1 minus pi times the natural log of wealth in the bad state. I substitute 0.75 and 0.25 in for pi and 1 minus pi, and I get a number for my expected utility, 11.45714. I know there's a lot of digits. That's because when you do natural logs, it smushes stuff. So that's without insurance. Suppose this agent was given the opportunity to buy fair insurance. Like I said, fair insurance in the real world doesn't exist, but let's suppose he did, right? Where he could keep his wealth equal in both states, right? So in this case, I'm going to assume that this fair insurance costs $5,000. So I pay $5,000 in either state. No matter what happens, I pay $5,000. If I end up in the good state, I end up losing my $5,000. But if I end up in the bad state, I get $20,000 back, or I net $15,000 because I paid $5,000 for my insurance. They gave me 20. I come out 15,000 ahead. And in both cases, 80 plus 15, I get 95,000. So my expected wealth, right, is 95,000, which is, right, my expected, my expected wealth if I didn't have insurance. But in this case, my expected wealth with insurance, right, is certain. In other words, I get 95,000 no matter what. So with the fair insurance, right, PG times WG plus PB times WB is equal to 0.75 1,000 plus 0.25 80,000, or 0.75 times 95,000 plus 0.25 times 95,000. They both equal 95,000. But I prefer this, right, because I get 95,000 no matter what, assuming I have that utility function. So in this case, I just simply take the natural log of 95,000 and I get 11.46163, which is greater than the uninsured case. So my utility increases, right, when I'm able to buy fair insurance. I get more utility, or this risk-averse agent gets more utility, right, if he's able to buy fair insurance. Let's suppose he was able to buy unfair insurance, where the insurance company actually makes a profit off you, on average. So now consider the case where instead of $5,000, right, I pay $5,200, and what I get in the bad state is $4,800. So in this case, in both states, I get, instead of 95,000, I get $94,800, right? in both states, and that $200 is the insurance company's profit. So in this case, the natural log of 94,800 is just 11.45953, which we see is right in between the other two cases. It's less than having fair insurance, but it's still more than the uninsured case. So in this case, at least at that price, at $200, right, above fair insurance, I still buy insurance. And we could keep increasing that price until we get to something close to the uninsured case, and we can see how much he's willing to pay for that unfair insurance, or how much of a premium is he willing to pay to get that unfair insurance, right? And finally, suppose that instead of the insurance company charging them extra, that instead that when you end up in the bad state, you have to pay a deductible, right? So you still, right, in this case, instead of paying $5,000, I pay $4,900 or $4,900. So in the good state, I'll get 95,100. In the bad state, 80,000 minus my insurance premium of 4,900, plus they give me 1,900. That's a 20,000 plus, but I have to put up to get even $1,000 of my own money. So in the bad state, I end up with $94,100. That's my deductible, that $1,000 difference, right? So in the good state, I pay 4,900. In the bad state, I still pay the 4,900 premium and receive $19,000. The $19,000 is a $20,000 loss in the bad state, less the $1,000 deductible. So in this case, my expected utility is 0.75 times $95,100 plus 0.25 times the natural log of $94,100, or 11.46. Now, this isn't as good as fair insurance, right? But it's better than the unfair insurance, and it's better than the excuse me, the uninsured case. Now, I can mess with these numbers for the deductible and for the unfair insurance, and I could probably switch them. I make a bigger deductible where he pays probably closer to $5,000, and the other one paying less, and I can switch them, or I can do all kinds of combinations to get the unfair insurance with or without a deductible, one preferred to the other. But in general, the insurance, as long as it's not overpriced, is going to be utility improving for the agent, and as long as you're risk averse. If you're risk seeking, you probably wouldn't want the insurance. So if I had a utility function where they're risk seeking, they wouldn't want it. If they were risk neutral, the only insurance they would buy is the fair insurance. Perfect. Okay. Questions? Okay. So this is it. The final course of ed. This is very similar to what we had before. Okay, what is the slope of this budget constraint in this case? Price of P over price of B. Perfect. Right? But in this case, I have two different consumers with slightly different utility curves, right? And I can see here that agent 1, U1, is more risk averse than agent 2, right? And agent 2, right? Agent 1 is willing to pay more of an insurance premium than agent 2 in this case. In other words, I'm willing to pay more to have more wealth in the bad state. I'm willing to give up more wealth in the good state. And agent 2 is, of course, willing to pay less of a premium. So he wants more wealth in the good state and less wealth in the bad state. That's not quite true. His utility says that he's not willing to pay the extra to get those two even. right? And he's just hoping that he ends up in the good state. I apologize for those of you guys who came in late. As I said, the lecture was going to be short. It is, of course, on my